So, actually we were teaching in the last class generating functions. Okay. So, you remember, and important results of generating functions like z1 and z2. Okay. So, what was z1 x or what was z1 g g0 dash x and z2 g0 dash x or x is equal to 1, and this was at x is equal to 1. A little, can you say what was it? Was g0 dash 1 and g1 dash 1. From there, then you simplified and got this. Okay. Do you remember? So, what we got is, again I do z2 a little. So, it was d dx of g0 g1 x at x is equal to 1. Okay. From there everything came. Okay. So, now what I want to, what can be the natural extension, that I want Zm. I can want Z3, Z4, Z5. So, I want Zm. Okay. So, let us think Gx to the power m, and Gx not to the power m, m is G0, means we can show it recursively that this will happen, G1 x. Okay. Okay. Yeah, Gm is this will go for m times, means I am just writing Gx 1, that time it came G0 G1 x. Okay. Then what you took? You took the d dx and you got Z1. So, this one and this one are related. Okay. Just I can expand and I can go on, because what we got is, from this was G0, this was G1, if you remember. Again if I have to go one more step, that will be G1 square. Okay. If it is G0, this is G1, again if we go one step, it will be G1 square. So, from there we do not do it, but from there this recursive equation comes. Therefore, what happens is, if I do d dx of g x to the power m, then what will that give? That would basically reduce the power by 1. Okay. So, that would give us G0 m minus 1 G1 x. Therefore, and instead of going 1, just 1 will come out. Okay. That can be shown. And then what happens is Zm is equal to, then it becomes G1 dash 1 into I am making a mistake. Let me do it in a better way. See, Gx can be written in this way, G0 x, when for m is equal to 1, no problem, and G m minus 1 Gx for m greater than 2, greater than equal to 2, no problem, just each time one extra. Am I think it is okay. See what was Gxm, it is G0, G1, G1 x. So, basically how many times G1 has come? M times. So, I am telling G1 Gm minus 1 is G1 has come m minus 1 times and you are adding just 1 x. Okay. Okay. So, now if you take Zm is what? D dx of Gm at x is equal to 1. Basically, you are taking this differentiation Zm, and that gives you what? Tell me, that gives you, because there is inside G1x will, I will come out, the most inside G1x will come out. Okay. So, just G1 dash 1 and whatever is left G m minus 1 dash 1. Okay. And G m minus dash 1 is basically Z m minus 1. Okay. So, this can be basically done recursively, and what we will get is G1 dash 1 to the power m minus 1 and G0 dash 1, and this is G1 dash 1 is what? Is Z2 by Z1. If you remember that G1x is 1 by x, 1 by z, G0 is kpk. What is G0x? Please remember and tell me. What was G1x? Please remember and tell me. 1 by z into kpk was there. So, that was G0 dash x. Z1x was 1 by z okay. Just to revise, what is Z1x? What is it showing? It is showing the outgoing distribution of a node when you are reaching that node by a random edge, and that depends upon two conditions. What is, how does it depend? It depends upon the degree of the node. Why? Because higher degree gives higher chance of reaching it, degree of the node and probability that degree. So, it is kpk. So, kpk comes from, if I have G0x, if I take differentiation of G0x, I get kpk. Okay. So, remember, that is why you have G1x. Okay. And with this algebra, what you get is Zm is equal to this one. Okay. Clear? Okay. So, now with this Zm, what can I ask? I can ask that what is the diameter? I now want to ask what is the diameter of the network. Okay. So, can you tell me using Zm how can we find the diameter of the network? Using Zm how can we find the diameter of the network? So, if I start from a what is diameter? If I start from a node, okay, I go one step, and if I complete the entire thing, then what is the diameter? Then what is the diameter? 2. 2 you have to 2 nodes, or you say 1. Yeah, you say 1, sorry, okay, you can say 1. Okay. If you go one step, it is 1. Okay. So, if I have to go to up till 2, then it is 2 steps. Okay. 3 steps. So, now tell me how to define diameter. If you have one node plus you have Zm. Okay. You have one node plus Zm, and summation of, tell me, m is equal to 1 to L should be n, means within that number of where n is total number of nodes. So, what is diameter? Again, conceptually let us think what is diameter. So, if I take this, I go to neighbors, okay, and if within one step I can reach all the nodes in the network, then I say diameter is 1. If I take 2 steps to reach the entire network, then diameter is 2. So, if I take L steps to reach all the nodes in the network, then diameter is L. Okay. And if I traverse L steps, what are the number of nodes I cover? I cover myself and all the first neighbor, second neighbor, up till Lth neighbor. Am I correct? Yeah. No, it is 1, for 1 it is fine. No. We are thinking it is a random network. So, you can say that this is the uppermost, this is the lowest bound or average bound. Okay. So, for some node it can be more, for some node it can be less. This is your proposition. So, we are picking, the idea is we are picking up a random node. Okay. And what we are seeing? We are seeing basically the distribution. So, we will get the average case. Okay. So, again this is a random network without any sort of eccentricity. Okay. It is not that there is one chain, means it is not that this is a network like this and there is one just a tail. Okay. You can have a network like this. Huh? You can always have a network like this, where the diameter is average diameter and means average distance between 2 and the diameter are totally different. Okay. So, what we are actually concentrating here is that we think that average distance and diameter are more or less similar. Okay. We are not considering eccentricity. Thank you, the question is very good. Okay. So, then what happens is, again I write this. So, let us, what is Zm? What did we find? Zm is Z2 by Z1 m minus 1 to Z1. So, let us put that. So, then with this becomes 1 plus Z1 plus Z1 z z2 z1, this way it goes, plus z1 z2 z1 to the power L minus 1 is equal to n. Okay. Okay. Clear? I hope this is clear. KK, this clear? Q, from just see this, you have m is equal to 1 to L, clear? So, this is just a simple series. So, you can go on solving this series, take this here, okay, and this part is Z1, you can see this Z1 comes common, and you have a GP series, and GP series is 1 by Z2 by Z1 to the power L 1 minus Z2 by Z1 is equal to n minus 1. Okay. And you can make this subject of the equation Z2 by Z1 to the power L is equal to 1 minus n minus 1 Z1 square Z1 minus Z2. Okay. And accordingly, you find that L is I am just writing the big equation, but you need not worry about this. Z2 minus Z1 Z1 square minus log Z1 square by log Z2 by Z1. Okay. So, this is extremely big, but if we think that and Z2 greater than, which is true, that number of nodes will be high. Okay. Total number of nodes will be much more than the second neighbor, and number of second neighbors are higher than the number of first neighbors. Okay. If you take this, you will see L is equal to log n by Z1 log Z2 by Z1 plus 1. Yeah. You are thinking it's an expanding graph, that it scales to its multiplies. Yeah, means if this condition holds, it may not hold for all graphs. I am not telling that it has to hold for each graph. Otherwise, this is the exact equation you have already got. I am just trying to simplify and make it, means this looks untidy, a little untidy. Yeah? So, I am just trying to make it a little neat, so that we can understand the significance. Otherwise, you really get lost in a big equation. Okay. So, this is how you get L. Okay. Now, can you tell me what is beyond all the jugglery, all the algebra, what is the significance of this equation? What did we achieve when we get this equation? Yeah, diameter is logarithmic, perhaps. So, that was already known, that all random graphs scales to, means its diameter scales roughly to its logarithmic size, logarithmic to n. Okay. So, it is a much more exact result than that. Okay. So, let us think from, if I think from like distributed computing, okay, or distributed processing. So, what are the things we are getting? What is this? It's a global parameter. Okay, this is a global parameter. And what are this? These are local parameters. So, you can simply visit a node, get its first neighbor and second neighbor. Once you know this, you know the diameter. So, that is the beauty, that if you just, so what you have to do, you have to just see the first neighbor and second neighbor, immediately you know the diameter of the nodes.
So doesn't it also signify that in L hops we can reach all the nodes?
Yeah, that is the diameter, that within L hops you can reach the nodes, all the nodes. Okay. So, that there lies the beauty of this, that a global parameter, yeah, it is an average case. Yeah.
Also depending on which node we are taking for Z1 and Z2.
Yeah, that we have said, that we are taking a random node and we are thinking that the average case does not differ too much from the, see, it does not depend upon which node you are taking. What is Z1? Z1 is not depending upon this node or that node, Z1 is average. Okay. So, that way it's, we are taking the average case. Okay. Z1, Z2 all are average. Yeah, average of all the nodes. Okay. So, I would not say diameter, but I would say basically average distance between node we know now.
But isn't this increasing the complexity? Like you go to every node, find out Z1, Z2.
No, no. So, you are just finding Z1 and Z2.
Z1 itself is an average of all the nodes.
Yeah. So, you do not find Z1, Z2. What you can do, basically you can sample 2, 3, 4 nodes and take their Z1 and Z2 and take the average, and then you can say that this is approximately the global average. Okay. So, the point is just like what happens in many cases, what you have to do, you have to re-engineer. Like one of the important problems in peer-to-peer networks is you any new peer-to-peer network is appearing and you try to understand how is Gnutella working, how is BitTorrent working, how is so this way maybe how is DC working, means anyway you try to re-engineer. So, this re-engineer, when you try to re-engineer, this type of rough assessment helps you a lot. Okay. It is not an exact assessment, but it is an assessment. Okay. Means you can say something very close, you can say something very close. Okay. Okay. So, this is good. Okay. Now, we go to bipartite network. So, we know bipartite network. So, there are two sets of nodes. Classical example of bipartite network, movie actor network. Okay. We can have actor, we can have movie. That our edge is there if an actor has acted in a movie. Okay. Yeah, so all those actors have acted in the movie as the edge, but an actor cannot act in another actor.
One movie is not
Okay.
related to another.
No, no.
Relation is not acting. Okay.
Relation is acting. So, a movie cannot act in another movie, an actor cannot act in another actor. ठीक है? Okay. Very good. So, this is a bipartite network. Okay. What is the obvious extension of a bipartite network? Multipartite, okay, fine, but yeah, Arithra, what you were saying? What is the network of a bipartite network?
Multiple partites.
No, not multipartite. You can always have bipartite, but what can you derive from a bipartite network? A unipartite projection. Okay, you can always derive a unipartite projection. Like I can have coactors network, okay. You can always derive a unipartite projection, coactors network. Okay. So let us say that average actors mu movies and average movie has neta actors. This is neta, huh? New, okay. Mu and nu, okay. So actors, okay. So if this is n and this is m, then what we can say, n mu is equal to m nu. Okay. So what we can say that 3 are independent, the fourth one is not. Okay. If these are the 4 variables, 3 variables are independent while the fourth is not. Okay. So now let us try to write the degree distribution of actors like f0 x, the degree distribution of actors. So that will be summation of pj xj for all j's, the degree distribution of actors, like we did g0 x, it is f0 x. This is generating function x. We are writing the generating function for the degree distribution. Okay. Generating function signifying the degree distribution of actors. I hope it is okay. P0 x to the power 0 plus P1 x to the power 1 plus P2 x to the power 2. This way it goes. So what happens is, 2 actors, what is the probability that an actor has acted in 2 movies? What is the probability that actors have acted in 3 movies? This way this goes. And what is G0 x? Will be basically QK XK. Means this is movie generating function signifying actor intensity in movies. Okay. How many actors have acted? So there will be some movies where there will be no actors. Okay, then there will be some movies where only KK will be there. Okay, so 1 actor, then 2 actors. Okay, very good. So you have the generating function. No problem? Okay, very good. So now tell me, and we know that f01 is equal to g01 is equal to Harsha is equal to one, because it is P0 plus P1 plus P2 plus P3. So all sum of all probabilities, basic, okay, elementary. Okay. Okay, clear? Okay. So now I want to show, and now what is f? Let us try to write what is f1x. Same 1 by from the old thing, why no f0, sorry, f0 dash x, okay, and g1 x is 1 by mu g0 dash x. This again the same thing. I find g1 from g0, I find f1 from f0. Any problem? Okay. Okay. Now I think in terms of coactors. So this is bipartite is clear. I think bipartite is pretty simple. Now I think in terms of coactors. So I want to find. Okay, I draw this. Okay, I first take this and say that I am here. Okay, and I want to find how many actors have coacted with me. Okay, how many actors have coacted with me. So what happens? Basically, that is my, what is that? How many actors have coacted with me is what? Neighbors of they are second neighbors. Basically, my coactors are my second neighbors. Okay, my coactors are my second neighbors. Clear? Okay. So we did this H0x, H1x. If you remember that, how to go to second neighbor, how to go to first neighbor. We will just use that. Okay. So have this again. As movie and as actors and movies. Okay. Perfect. Okay. Now I can reach here. Okay. What is the outgoing degree distribution of this, of if I reach any node? Yeah, what is the outgoing degree distribution? From what is G1x? What is G1x? Again, let us try to think. What is G1x? G1x is if I pick up any random edge and come to movies, then what will be the outgoing degree distribution of that movie node? Okay. See, that's how comes, because you are not attending class. Okay. So what happened? If you again we go back to our old thing, what was happening? Remember this picture. What is G1x? That you can come k pk x to the power k minus 1, because it's outgoing edge. So the edge which you are coming has to be moved, and then by z. This was G1x. You remember? So what was G1x showing? Again, G1x was showing that if you come from a random edge, then what is the outgoing degree distribution of that node? Okay. And if you come from a random edge and come to a node, then what is the outgoing degree distribution of that node? So you have a random edge, you come to a node and you want to know the outgoing degree distribution of this, and that was characterized by G1x. Okay. Yeah, it can have anything, but this is what G1x is. I am not telling it in terms of bipartite, I am telling in terms of unipartite. What is G1x? I am just trying to tell that. Okay. So you come from a random edge and visit a node, this is our knowledge in unipartite or our knowledge in normal networks, that you pick up a random edge, you come to a node, and what is the outgoing degree distribution of that node. Clear? And that depends again, that depends upon two factors, its degree distribution and its probability of reaching that node. And if it has k nodes, k edges, then its probability increases k fold. That is why you have two factors, k and pk. Okay? Okay. So, now again let us see. So, you are here, you come here, okay, and then you go there. You from here you try to see the outgoing degree distribution. What are you trying to see? If I am trying to see my coactor, basically from an actor node you are coming to a following an edge, you are coming to a moving node, and from that moving node you want to see the outgoing degree distribution of that moving node. You are correct? Am I correct? Okay. So, that is immediately what G1x.
It can be F2x also.
Yeah, we will try to see why. Means somehow it will be related with that, but I am trying to write it in terms of 1. Okay. We do not go one step further. Okay. So, I am trying to write it not in F2, but I try to write it in G1. Okay. So, G1x. So, what happens is it can, what we know, that picking up a random edge is equivalent to picking up a random node and traversing a random edge. Okay. This is what we have thought as equivalent, means there are controversies perhaps, but this is what we have thought as equivalent constantly. So, what happens is, so you can, so now it depends, if you pick up a random node, then what will happen? It can have one edge, then P1. So, one edge will reach you to one node. So, that is giving, and that node will give you this distribution. It can have two edge, then both of them will behave independently and give you this distribution, and you can have k nodes and all of them will behave independently and give you this distribution, and that is basically giving you the G0x, where what is the G0x? What is G0? Why am I writing 0?
Because it's like F0 of G1x.
No, this is the degree distribution of the unipartite projection. Say G0x, what I am writing G0 is the degree distribution, think this way, degree distribution in a coactors network. Basically, from the bipartite network, I am constructing a unipartite network, okay, and I am trying to write the degree distribution of that unipartite networks. That is why I am writing G0x. Okay. Am I clear? Okay. So, I repeat it once more. So, what happens is, what is my objective? KK, what is my objective? I want to find, if I am a node, what is the degree distribution of my coactor. What is that essentially? If I have a coactors network, the degree distribution of the coactors network. Okay. So, now if I want to find my coactor, what I have to do? I have to traverse one step, okay, and see, I have to traverse one step. If I traverse one step, since this is a bipartite network, I necessarily reach a movie, and I have to see the outgoing degree distribution of my movie. Clear? So, if I traverse one step and if I traverse one step, what is that? That means to this movie node, it means as if somebody has picked up a random node and reached that movie. Okay. And so, the outgoing degree distribution of this movie node is G1x, and I can have one node, 1 edge, 2 edge, 3 edge. Accordingly, I write this generating function. So, this is basically what is this? F0 G1x. Hmm?
Two movies we are going from particular actor.
Hmm.
They can have again same actor. So that will be
Yeah,
different.
they can have same actors. So, what is the problem? For each movie, they cannot have two actors. Means unless you compare, give weights that this guy has acted in double role. Okay, it doesn't matter. Okay.
So I still don't understand how is it, how could you replace x by g1 of x? Like, how is it f0 of g1 x?
See this one.
How could you get this p1 of p1 into g1 x? How did you get p1 into g1 x?
Because I know the probability of having one node, and as soon as I reach that node, I know its degree distribution, that is G1x. As soon as I reach a movie node from a random edge, I know the outgoing degree distribution.
So in f0 of x, x is a degree distribution.
Which one?
f0 of x.
No, I don't have f0 of x. I have f0 G1x.
In f0 of x,
Yeah, in f0 x.
x is a degree distribution.
X is not a degree distribution. The coefficient of x signifies
The probability.
the probability of the degree.
What is x?
X is nothing. X is a generating functions variable. So, what we have shown that with this variable you can do a lot of work. It's a mathematical tool. X is a mathematical tool. It doesn't have any physical significance. Only significance is the power x to the power, the coefficient of x to the power k tells the probability of having that property k. Okay. Means k may be degree property, k may be means x may be signifying various properties. Okay. So, this is clear. Okay. Now, let me ask you one question, one more question, that I want to find G1x now, means G1 of this G0x. Okay. So, tell me what will happen. So, tell me physically what will happen first. Can you tell me physically, if I want to find G1x, what I have to do in this bipartite distribution? Huh? No, first tell me physically what is that?
Is the actors who have acted with my co-actors.
No, first you pick up a random edge. What is G1x? You pick up a random edge and then you reach a actor node, and then from that actor node you see that from that actor node again you traverse a movie node, and from that movie node you see the outgoing degree distribution. So, what extra will come here?
F0, G1, G2, F2, G3.
No. Okay, again. Let us think again. Let us think again. That I pick up a random edge and I traverse, I reach a movie. As soon as I pick up a random edge, if I am intelligent enough, or means within 2 chances I will reach a movie. Okay. Either I will reach a movie or I will reach an actor. So, let me reach an actor. Okay. Once I reach an actor, I do the same thing which I have done here. What I do? I traverse and reach a movie, and then I see the outgoing degree distribution of that movie. Okay. Clear? So, now tell me, what can be this G1x? What extra will come here? So, reaching here was not considered previously, so but it has to be considered. So, you can just put kp1 G1x, because you can reach means 1 into p1 G1x plus 2 into p2 G1x square plus k into pk G1 x to the power k. Okay? Because it is just that now reaching that node is proportional to the degree of that node. Okay. So, that comes, and this we know again is f1. Last one, is, so I write this in a better way. So, G1x is what? 1 into P1. Okay, I have 0 always. So, let me write this. Plus 1 into P1 G1x So, what is happening? See, you can reach, everything stays same. Once you reach this node, everything stays same, but in order to reach that node, means the probability of reaching that node is proportional to its degree, because if you have a k degree node, then if I pick up a random edge, you have k times more chance than if you are a single degree node, the old concept. Okay. So, with everything you have this multiplied. So, this becomes actually k pk summation of k pk G1 x to the power k, k is equal to 0 to infinity. And what is k pk? F1. So, this is F1 G1 x. Okay. Is it clear? Karishma, that's okay? Okay. Good. So, now I want to find Z1. Now, I want to find Z1. So, what is Z1? Is Z0 dash 1. So, what is G0? Let me write here, G0 x is F0 G1 x. So, G0 dash 1 is G1 dash 1 into F0 dash G1 1, G1 1 is 1. So, this become G1 dash 1 into F0 dash 1. Okay. And what will become Z2? Again we know Z2 is Z0 dash 1 into G1 dash 1. So, Z0 dash 1 is already written there, G1 dash 1 into F0 dash 1, and what will be G1 dash 1? Tell me, Varun, tell me what will be G1 dash 1, see this and tell me. F1 dash f1 dash g1 1 into g1 dash 1, and we know f1 g1 1 is 1. So, what we can write f0 dash 1 f1 dash 1 into g1 dash 1 whole square. So, what is happening exactly? That you are actually dealing with a bipartite network? No, you are not dealing with a bipartite network. You are dealing with a unipartite. This is of all the unipartite networks. We found it for what are for this the coactors network. We are finding everything for coactors network. Am I okay? We are basically finding everything for coactors network, and for coactors network you see you find Z1 Z2, but using what parameters? The bipartite parameters, using just the bipartite parameters. Okay. So, you derive. So, now what you were saying about multipartites. So, this theory can be further extended, that you can have multipartite networks, but you can derive the degree distribution and other properties of its lower partite projections. Okay. Okay, great. So, the last question which we can ask is giant component. So, what is the formula for giant component? So, I just do a review. What was we are doing? This was that average component size, if you remember. Okay. We found this was the average component size, and when do giant component arise? Subhash, when do giant component arise? When do giant Madan, when do giant component arise? Huh? When this becomes infinite, and it can become infinite when this part is 0. So, we know giant component is Z1 dash 1 is equal to 1. Okay. So, what is Z1 dash 1? We have already written what is Z1 dash 1. What was Z1 dash 1? This part, This part is Z1 dash 1. F1 dash 1 into G1 dash 1 is equal to 1. Okay. And what is F1? F1x is 1 by mu F0x or something like F0 dash x. Am I correct? And what is mu? F0 dash 1. Okay. So, let us write this 1 by mu F0 dash 1 F0 double dash, it will become F0 double dash, okay, and this becomes, this is same 1 by nu G0 double dash 1, and this is equal to 1, and if I take this that step into this is what is this F0 dash 1 into G0 dash 1. Okay. Okay. So, what is again, let us see what is F0x. Am I is this step okay? Okay. What is F0x? Pj x to j summation, if you remember, and G0 x was Qj Qk x to the power k. Okay. Okay. So, let us do the differentiation quickly. F0 dash 1 will give us j Pj summation. Yeah, I did 1. So, x to the power will go, and F0 double dash 1 will give us j minus 1 Pj. Okay. Okay. So, now using these things, let us rewrite this equation. Using this thing, let us rewrite this equation. So, this becomes what? There is a summation j Pj j minus 1 Pj, I write jk, okay, and k minus 1 Qk. I took the summation overall and take this side. This is Pj into Qk into j into k is equal to 0. Just I have taken this to multiply everything together. Okay. Okay. I think this is simple, because this is j minus 1, k minus 1, and here just jk. So, this becomes Pj Qk j k minus 1 minus jk. So, this if you do a little bit, jk Pj Qk, jk comes common, see jk comes common, then j minus 1 k minus 1. What is j minus 1 k minus 1? jk minus j minus k plus 1, and from here a minus 1 comes. So, this gives you this Pj Qk jk minus j minus k. Okay. So, last question, seeing this equation, can you tell me something about co-movie network? Huh? See this is a symmetric equation, symmetric in terms of j and k. So, if I take a co-movie network, it will also have same percolating condition as a coactor network. Okay. It will also percolate at the same point as a coactor network. Okay. So, I think generating function is clear. Tomorrow we will take generating function and see how churn in network can be modeled. Okay. When network breaks down, how churn in networks can be. Okay. Thank you.